Hello, everybody. We're going to be working on Chapter 1 tonight. We're going to be going through the first chapter of our textbook and talking about some important concepts and kind of get us moving forward on this course, getting into some actual material. The author of the book does provide his learning objectives here that we are going to talk about. I am going to pepper in some of my own kind of, computer history things mostly near the beginning part of this, and then I will tie them into what the author is doing. And in fact, I think I'm going to start with my own computer history stuff first because I think they get into this concept of like computation's 8 big ideas. And I tend to agree with all of these as being some of the more important, advances in computer technology, that we're learning about and information technology in general. However, there's stuff that did come before this that I think is relevant and important to talk about. Now, Cindy Lou, I know that you've had classes with me before, so you may have heard some of this lecture stuff way back when, and perhaps not. Maybe you didn't have those classes with me. But I always like to mention to people that, the idea of people working with both information and technology to allow them to do advanced things that we could not do without, conceptually has really been around for millennia. We are smart people, and we've developed a lot in a couple hundred years because of the industrial age, but we really still stand on the shoulders of all the brilliant people that came before us that didn't have all the advantages that we have, where we can rapidly develop things in a way that they never could. They might be able to think about it and envision it, but never really could actuate it. We have the difference now that because we work largely in a virtual capacity, that we can construct and concoct things virtually to test them before we even build them in reality. And that's a significant advancement in human history, really one that's fresh, really within the last 50 years. So we are going to come back to these ideas, and once I do my little spiel and we come back to it, you'll see how it all ties in together. But I'm going to begin by actually taking us out to a web browser. And, at this point, I would ask that you just kind of watch your screen and follow along with me. But I'm going to start with what, a lot of people consider one of the first computing platforms, and it's called an abacus. And I'm not even sure I'm spelling it right here, but many of you may have even learned how to use one of these. And I know that when I was in elementary school, and that, it's kind of strange because I know a lot of people didn't have this experience. We did, a unit in one of my 5th or 6th grade classes where we were taught how these things work, and basically the operation of an abacus is like this. You notice that there's usually 5 beads and then there's 2 beads up top. So you count up to 5 and you push one up. You count up to 5, you push the second one up, and you got 10, right? And then you can kind of figure out you can keep doing that. And really what the Chinese kind of did when they developed this is they recognized, well, I got 5 on one hand and 5 on the other hand, put it both together. So the beads kind of represent your fingers and hands. And I think it's brilliant, right? Fascinatingly, if you've ever watched somebody work an abacus, and this is the thing that blows my mind. When I was a younger person, my dad used to be, kind of jokingly in the import-export business. He would import products from Europe and bring them over to the States and sell them. And he would work all these trade shows, and every once in a while he would do McCormick Place in Chicago, and he would bring me with, and I would sit there in his booth and help to take orders or just watch things, But right across the aisle at McCormick, there was a Chinese import company. And they would sit there and take orders from people, and they would write them down in a book, and then they would calculate the total for the order. And they didn't use a calculator. They were just flipping the beads around, and boom, 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 they would have the answer. And it astounded me to watch them work, just as much as it astounded me to watch my dad do math, where he learned to do math on his feet in the marketplace in Greece. So they had a fishing fleet. They'd bring in the fish. My dad would take the fish off the boat, and they'd take them into the shop. And, they would, determine whatever the price should be, 50 drachmas per fish or per kilo or whatever, their unit of measure was. And all they had is a scale. They didn't have a calculator. They didn't have a thing where you could type in the price per weight, and it tells you what the answer is, like, a modern butcher would. He would have to do the math in his head. And I would watch him tabulate things, and they were just really fast at just, because they learned in a traditional mathematical way to add a column of numbers faster than any one of us could even type it on a keyboard, and be more accurate in some cases. And the abacus is one of those tools too. So to think that human beings have been really smart lately, where we all lean on calculators in Khan Academy to know our math, people in the ancient world were doing these things a long, long time ago, and they were pretty astute at it. And if you think that the abacus literally goes back thousands of years, and that people were able to operate these devices and do pretty advanced calculations with them, is pretty mind-blowing. Now, as we fast forward into the future, we went through kind of like the golden age of the ancient world, and Rome came up, and then we had the Dark Ages. And a lot of knowledge, frankly, was lost, especially in Europe and around the Mediterranean, for a number of different reasons. Fortunately for us, the Arabic world maintained a lot of the Western records in their archives, and most notably in Babylon, by the way. And they, kept the light alive, so all the ancient teachings and writings were often preserved there. And the Arabic peoples came up with quite a revolutionary thing on their own, and that was the base 10 number system. And all the math that we do these days, are basically the Arabic numerals. I mean, they're the ones who invented this branch of mathematics and the number system, because prior to that, the only thing that we had really of note to note numbers was the Roman numeral system. And if you've ever worked that, you know how tricky it is. Very hard to do math with, because it's very illogical. And so we're coming out of the Dark Ages, we're going into the Age of Enlightenment, and part of it was where the Western world was regaining their knowledge that was lost, thankfully preserved by people in the Middle East, right? So they got a lot of the knowledge back, and we started opening things up. And there was this invention that happened that was really important, called the Gutenberg Press. So let's talk about that. See if I can spell it right. Yes. And the Gutenberg Press was basically a machine that allowed people to put little pieces of lead type into a machine, run ink over them, and then press it down onto a piece of paper. Now you have to keep in mind here that prior to this time, very, very few people could read, right? And basically the ones that would learn how to read would be typically people in the clergy, people who were in positions of power and can afford to educate themselves. And because of that, the common people never really knew, for example, what was written in the Bible, because they couldn't read it, right? And so when the Gutenberg Press was invented, what was the first real major publication? They started printing the Bible. And it's no wonder that shortly thereafter there was like the Lutheran Reformation and all those things happening, because now you could get the book in your hands and read it for yourself. So instead of listening to some preacher up on a podium say, hey, this is what God said, you're like, wait a second, it doesn't say that at all. You can think for yourself. Now also, when people started to read and use this press, the information could be replicated. So I could print it not once but 1,000 times, put it on a piece of paper, and put it all around town, right? And hopefully they could read it. But the mechanics of this device, was important too. So you see like how it works. So it's a mechanical press. They have examples of this that are still working. And by the way, and the modern printing press business in industry really didn't stray far from this. I mean, they made it electrified, made it out of steel instead of wood and all that stuff. But it really didn't change, frankly, until the early 80s. This technology was still prevalent. Now, there are all these things happening during the Age of Enlightenment. We're talking basically 1600s and beyond. And one thing that happened is people were harnessing water power to automate mechanical processes. So we had mills that would drive mill wheels and make things spin, and you could grind your wheat with it, and all types of things like that. And there's this guy named Jacquard, and I'm trying to spell his name here. And what he did as a profession, by the way, is he was a rug weaver. So he would take yarn and fabric and whatever, and he would weave fabric. And if you guys have ever seen a loom in action, it basically is this thing. And if you're watching the video window here, if you see my fingers, where the strings would go like this, and they would shoot a string through, then it would alternate, and they'd shoot another string through, and then through that repeated action, they would weave a rug. And this guy was a master weaver, Jacquard was, and he lived in France, and the King of France one day saw one of his rug designs and said, "Oh my God, that's beautiful. I have this giant palace, I need 100 of those." And Jacquard's like, "They're all one of a kind. I don't know if I can ever do this again." You know, he didn't know how to recreate it. But what he did was something super, super clever. He combined the water power of a mill with what kind of looks a little bit like a Gutenberg Press, you have to admit. You know, it's like this mechanical device. So the loom was powered by the water power. And he came up, his revolution were these punch cards that you see on the screen. And these are made out of wood. And really what these were is a series of instructions of which color thread to send in at the right time in order to recreate the pattern again. And so he figured if he could punch the pattern into the cards and put them all in a sequence so they were all tied together, he could feed it through the machine, flip a lever, let the water power drive the whole thing, and he could always replicate that same rug. Now, for as primitive as that might seem, that the act of basically digitizing the information and putting it into a punch card is revolutionary, because really what he was doing, he was programming that machine to perform the same series of steps over and over again. And it worked fabulously, by the way. Now that idea kind of drove a lot of other thoughts in people's minds. So it's like, okay, so I can program this machine to perform repeated actions. What else can I program? You know, so that's the thinking. So let's fast forward then to this guy named Charles Babbage. And Charles Babbage was this guy, and you notice this is what he looked like, so it's kind of cool. Well, they have pictures of his machine here too. He conceptualized this thing called the analytic engine. So he looked at what Jacquard did with the mechanicals, and he envisioned that, could I take some sort of machine with a complicated series of levers and gears and somehow tell it to perform a mathematical calculation and then turn the gears again and then come up with an answer to the computation. Now, interestingly, he designed the thing conceptually, drew it out on paper, but he was never able to build it. In fact, he died before it could be actuated. But unfortunately for him, there was this lady named Ada Lovelace. And Ada Lovelace, and this is a picture of her, she came from a very wealthy family. And what she is credited for, folks, and sorry guys, hate to burst your bubble here, but the first programmer was Ada Lovelace. She was the first, what we call computational programmer. And in fact, her first program that she wrote and put out there, in fact, I'm going to find it here. I'm sure they have an image of it. So here's an actual image of the program. And if you click through and zoom in on this, and I'm going to try to do this. Of course, I zoom in and it gets smaller. Thank you. But the point is that this is what she decided. So she looked at Charles Babbage's design for the analytic engine and decided, I can write the instruction set to make that work. And so she came up with this. And if you could see this document a little bit closer, she came up with the whole concept of variables, instructions, how to take a simple on-off switches on a device and convert them into more complicated mathematical statements. So basically taking something complex and converting it to binary. And really wrote out a complete instruction set basically to solve this equation that you see up here, which is, one of those friendly little basic math calculations, right? Calculus in essence. Eventually they did get to the point where they built a working version of the device that was able to calculate, but unfortunately it was well after Charles Babbage's death. And they proved that they could make a mechanical adding machine that was simply a matter of like setting some switches and levers, turning a crank, and then getting an output, which was usually a series of levers flipped the other way or something like that, and then you'd have to interpret it. But it could do complex programs. So you could set up an equation, put different variables into it, and it would tell you what all the different outputs were. So it was a significant advance because prior to that, the only way to do that form of mathematics was either to use a slide rule or to do it on paper. And then good luck to see if it's right. All right, so why is that important to where we're going? Our book takes us, to this spot. And in fact, let me just go back to Google here, where we start to learn about Herman Hollerith. And Herman Hollerith is a very important character too. So what he did is he borrowed ideas both from Jacquard's loom and Charles Babbage's analytic engine and Ada Lovelace's programming, and married those into a concept. So what he was responsible for is he worked for the U.S. Census Department. And at the time, late 1800s, the United States was growing so quickly that they didn't know what to do with all the incoming people. And on top of it all, we had this like strange clause in the Constitution that said, every 10 years you must go forth and count every man, woman, and child across the land and send a report to the president, right? So that they knew how to allocate funds, how many seats of Congress there should be, et cetera, et cetera. Same issues we have now when you think about it. But the states were growing at such an exponential rate in the late 1800s, and then when you combine that with the fact that we went from being kind of like an East Coast country to a coast-to-coast country, with not very good transportation in between, these census workers would often take almost as long as 10 years to complete the process. And I think the book said that it took them like 8 years just to do the computation. But they also had to travel the whole country and knock on every door and ask everybody, how many people live here? Okay, thanks, bye. And they, he thought, well, if I could speed up the calculations, we have to do this every 10 years. We better figure out a way to speed this up because otherwise there's no way we're going to count everybody. And so he would take the information they would gather from the field people and he would punch them into cardboard cards. And those cards were basically digitized information about human beings. And then that was fed into the machine, which then used kind of the same algorithms that Babbage's machine used to give you a total amount. So you would put in a stack of cards and it would process it and it would give you some sort of a response. Yeah, exactly. And Derek put a little comment into the chat window, and they expected the next census to take 14 years just based on the rate of growth, which was nearly twice as long as what they had before, and that was untenable. And so necessity is the mother of invention, folks. So he came up with this idea, and he parlayed this whole concept into a private company called IBM, which, by the way, is still around, amazingly. So the primary way that humans were digitizing information, and some of you that are in the gray-haired club like me will remember the old days where punch cards were still used into the 80s, folks, as a form to deliver information to computer systems. And people would write their computer programs on punch cards. People would in some cases, I remember getting you'd get your gas bill from Wisconsin Gas, and it would be like on a punch card thing. I don't know if any of you remember that. I sure remember that from being a kid. But it was a very prevalent technology, and of course they had all these devices in place that knew how to read the cards and then transmit that into electronic information and then have it processed. And when we think about where we've come from in that regard, pretty darn amazing. Now, the whole process of adding machines and basically what Herman Hollerith developed kind of parlayed itself into smaller devices. So I don't know if you guys have ever seen things like this, where these are what accountants used to use well into the 40s, 50s, and 60s in some cases. These were mechanical adding machines, and notice the crank on the side. Right, so people would type in their numbers and they would turn the crank to do the calculations. They're really using the same analytic engine. It's all done mechanically. Amazingly, I think, when you start to think about it. But the process had started. Now the trick was, can we get the mechanical component out of it? Do we have to rely on the mechanics to make it go? And what they started doing is developing electronic computer systems. And our book very accurately and thankfully correctly identifies the fact that the Germans, England, and the Americans were all working on this problem simultaneously, and had all come up with their own working electronic computers. But most of them, the German and the British, were electromechanical. So they had electronic non-moving parts of it, and then they had the mechanical parts as well. And what was the revolution when you guys read about ENIAC is the fact that ENIAC was the first fully electronic computer that you could program a set of instructions into and then get a result from. And you can see all these various images of it. Some of these might appear in your book, but it was literally a room-sized computer that was built with predominantly this technology called vacuum tubes, which I'll put up on screen here in just a second. And you would program it basically by connecting different wires in a patch bay, or flipping switches, or turning lights on and off. And the vacuum tube was kind of the main electronic component inside of it that would drive it. And let me show you what a vacuum tube looks like. This is in your book, by the way, but no harm done in Googling it here. So this is a vacuum tube. It's akin to a light bulb, basically. It powers up. It does a little bit of electrical resistance and flow correction, basically, is what they do. But they light up like a light bulb, and they generate a significant amount of heat. So I forget how many tubes were connected to ENIAC, but I want to say it was in, I don't know, like some ridiculous amount, like 5,000 or 10,000 or something like that. And that would generate so much heat, if you can imagine being in a room with like that many light bulbs, that they had 5 central air conditioners cooling the room down so the thing could operate, not like, melt everybody to, I don't know, their essential components or whatever. Interestingly, when they were working with programming these machines, they one day were running a program. And so here's the people at ENIAC, and they ran the program, they checked all their settings, everything's correct, and then they had to start ripping the machine apart to figure out something's not working here, why is it not working? And it turned out that in one of the tube sockets, there was I think it was a moth, that's kind of what it looks like there, got stuck, and it was shorting out the terminals on the vacuum tube. And so there was a bug in the system, or a bug in the program. And that's where that whole term comes from. And in fact, they found the bug and they taped it into their log. And so this is the first, and it says right here, first actual case of a bug. Right there. And it wasn't because they made a mistake programming, it was because there was actually a bug in the program. But when we write computer programs today, we use that term. We say debugging, because we're removing the problem out of the program. And I think it's just fascinating. We very quickly moved from this age of vacuum tubes, though, into what I call a very miraculous invention, which is the transistor. And the book talks about this too. So we go from this thing that's the size of a light bulb and generates, you can cook your bread with it pretty much, to this thing that's like a fraction of the size, like 1/100th of the size, and does exactly the same electronic function without the size or the heat or the draw of electricity that a vacuum tube would use. And then that single transistor then became revolutionary, by the way, absolutely revolutionary. So like we saw like radio sets that used to be powered by tubes now run by transistors. And now you could put a radio in your pocket instead of having this big console in your house. Or the even more miraculous invention of the integrated circuit, where they figured out how to take multiple transistors and put them onto the same silicon wafer. And some of these, like the more basic ones like this, where this is probably like a 8-bit or 16-bit integrated chip, so there's 8 transistors in there, we move very quickly from integrated circuits up to CPUs, where CPUs are basically the same technology, but literally have billions and billions of transistors embedded on something that you can hold in your hand. And most of this here aren't the transistors, it's a little black part in the middle that's the transistors. And there's billions of them. And because they're so small and so thin and so efficiently put close together, it draws very little power, generates very little heat, and really is responsible for the explosion in technology that we have today. There got to the point where, that we thought we had reached our theoretical limit on how fast we could even make processors, and this was 20, 30 years ago, folks, but they still keep finding ways to make them faster and faster and faster. They have all sorts of strategies. The fact that we have multi-core CPUs, that's a byproduct of all of this. And really, truly, the phones that we hold in our hand are the supercomputers of a decade ago. That's the kind of power we have now. So now I would like to pull us back to the book material. We did talk a little bit about the era of like the beginning of the first fully electronic computers, and one of the aspects of it that I always like to highlight is how many of you have ever been to the Museum of Science and Industry in Chicago and gone to the Submarine Exhibit? Has anybody done that? Okay, if you guys have not done that, you owe it to yourself to go see that, because it's a pretty miraculous exhibit. Basically what they have there in the basement of the building is a submarine that they captured from the Germans near the end of World War II. Inside that submarine was a device called the Enigma Machine. And maybe some of you have seen the movie The Imitation Game. And if not, I'm basically kind of suggesting that you watch that movie because I think it's very historically interesting. But this is an Enigma machine, and really what the Enigma machine was like a typewriter into which you would type a message, like any normal typewriter, but it had a set of gears and levers in there that they changed on a daily basis to change the cipher. So in other words, you would type one thing on the keyboard, and based on the algorithm of the gear setting, it would output a different message, and then that message would be transmitted over open radio lines. They couldn't really censor radio information back then. They couldn't encrypt it. And so they knew the enemy, the Germans knew the British could listen in, and the Americans could listen in, and then like good luck making sense of their message, right? And, so this was very problematic because the Germans basically had a way to send coded information to their submarines and whatever and say attack this or do that. And for a long time, the British were trying to crack it. They brought into the mix a man named Turing, and his name was Alan Turing, and he's basically the subject of the movie. But he came up with an electromechanical computer that was able to crack the code of the Germans. And the problem with the code of the Germans was it would be valid for 24 hours, right? And at 6 a.m. every morning, they would reset the codes, and then good luck cracking the code. So you had like 24 hours to crack it, and it was pretty intelligent on their part, right? That they would rotate the cipher. What burned them though was this: they ended up, every message they would ever send through the system would always end with the message "Heil Hitler," right? And once they realized that, then they had a basis for which to interpret at least the last few letters, and a basis to try to crack the code. And eventually they did. And they had to be very careful with it because they didn't want to give it away right away that they figured it out. And so they selectively would use it. But it is attributed to actually winning the war for the Allies. Because all of a sudden we knew where they were going to attack. We knew what they were going to do in the coded messages. And you can go see that movie. I'm sure you can download it. Stream it. I don't know where it's available. It looks like it's on YouTube and whatever. But this is, it's a dramatized version of this, but they do talk a lot about the mathematics, the technology, and then ultimately how Alan Turing was mistreated in the aftermath of it all. But his device was responsible for, in large part, winning the war. And the fact that you can go to Chicago and see one of these Enigma machines in person, touch it even, is pretty amazing. And, the other thing that happened is when they captured this submarine, now they had one of the devices in their hands. And then they really knew how it worked, and it really kind of blew the whole war wide open. It was like a really big deal, by the way. But another really brilliant mind in computer technology, and more importantly, his name is attributed to this thing we call the Turing Test. And I don't know if anybody's ever heard of this, but the Turing Test is a way of asking questions to an artificial intelligence to determine if it's an artificial intelligence or a human being. Isn't that pretty profound for somebody to think about in the era where they were working with electromechanical computers as opposed to even software at the point? And it's a fascinating concept. And now that we're in the age of AI, and it's coming down the line real quick, and a lot of us are already working with it on a daily basis. Like if you talk to Siri or Alexa or any of those devices, I mean, that's a form of artificial intelligence. The fact that you can, conceptualize this before the technology is even here is profound to me, and how prophetic of a thinker this person was. Very, very impressive. Let's jump over to that PowerPoint now, and once again, I encourage you to jump in and throw in ideas. And now we'll look at these big ideas, and maybe I'm hoping a little bit different light. So we did talk about the punch cards, and we talk about how long it took. So the punch cards, and being able to take information and digitize it. Now they're looking here at Herman Hollerith and his IBM invention, but really Jacquard is more truly the inventor of the technology, because Herman Hollerith strongly borrowed it from him. He also borrowed from Charles Babbage very strongly. But the process of taking that information and poking little holes in a card that represent the information that can then be processed, huge, totally huge. Next big idea is the fact that we could store programs for our computers as opposed to having to rewrite them every time. So when people would program ENIAC, by plugging in wires and whatever, it's not like they could just grab their USB drive and plug it in and load up the program, or a diskette even. They had to manually do that. So when we got to the point where we could store the programs and run them and then repeat them, absolutely revolutionary. And that era really came at the end of the 40s and into the 50s, by the way. And very quickly, banks, government, and big educational institutions were bringing these computer systems in just to help them crunch numbers. And by the way, the big reason we have ENIAC all together is because of World War II. And I don't know if you guys noticed the correlation there, but a lot of this stuff was developing then because we had the impetus to. The Germans were using their computers to do programming to figure out the trajectories of rockets and missiles and help them build their advanced technologies. And thankfully, Alan Turing figured out how to crack their codes, because if we hadn't, we'd probably all be speaking German right now, real sincerely. It was like that sort of on the razor's edge. And, got to put in historical perspective, the Germans had jet planes in the 40s. Nobody else did. They could go way faster. They had missiles they could launch from Germany and with great accuracy figure out their trajectory, force, speed, wind speed, velocity, all that stuff to land it accurately and bomb London without ever leaving their home. No wonder we stole all those mines and brought them here. But the Americans brought some of that, idea to this computer platform basically because it helps you do the computations faster to do those advanced mathematics where you can determine those things. So it helped us build the atomic bomb. It helped us get our own space program going. Huge developments. Once again, they talk about the transistors, absolutely huge, because we went once again from the vacuum tube down to these little tiny things, right? And ironically, Dennis, I'm looking at you because I know you play an instrument, right? Like you play guitar, and guitar players, of course, crave a tube amp, all right? And often we even look at the transistors that go into the pedals that we use, and those are coveted now too, because everything is integrated circuits, and it's thought that the transistors have a better sound than integrated circuits do, and they do, by the way, and it's mostly because the electrons can breathe. It's kind of an interesting thing. From there, we kind of moved very quickly into this era where we went from the mainframe era, where the 40s, 50s, and 60s were basically very few organizations had computers, and we move into the 70s, and all of a sudden all the universities are having computers, all the big businesses are buying mainframe systems, and soon enough we start making personal computers. So some of the very first personal computers are Xerox Alta, and a lot of people don't think of Xerox as a computer company, but they had some pretty profound developments, and that not only the first personal machine, but also the concept of a graphical user interface, which a lot of people don't know. The concept of a mouse came from Xerox Corporation. From there, we very quickly moved forward, through the 70s and 80s, through the age of personal computers and the Macintosh and all those things, to where the internet came to be. And really, the internet had its start. We talked about this last time in 1969, but it really didn't become the internet as we know it until the 80s, because it was really at that point a set of divergent networks that were all developing on their own. And the great connecting piece was all these, basically university students and hackers finding a way to get the computers connected to the phone lines to talk to each other across those separate networks. So like the military had their own network, educational places had their own networks, etc. They were still internets, but they were not interconnected. And so when we moved into that era, when everything was interconnected, late 70s, early 80s, by the way, we started seeing all the conventions that we are used to now, with the exception of the web. So we had email, we had FTP, we could go to chat rooms, we could have online user groups where people, like Reddit and stuff, where people would share information, on Usenet and all those things. By the time we got to the late 80s, there were some really revolutionary people like Tim Berners-Lee, for example, who were working over in Europe at CERN, and they would work with all these different computer systems, various platforms, but they had this need to kind of tie the stuff together. And he figured out a way to write a piece of software that would allow you to connect network resources from various sources and create links to it from one document, called an HTML document, a web page. Now, he did create the first web browser, but it was not graphical like what we see today. He created a text-based browser, and you would navigate around it with your keyboard, you'd arrow around, and then if you hit a link, you'd press enter, and it would take you there. But revolutionary nonetheless, because he took really what was a collection of separate ideas and gave you a way to connect to them all collectively with one fell swoop. Now, from there, we started doing some pretty advanced things. So we were writing software right from the beginning, but the formal high-level languages that we learn today really have most of their foundations back in the 50s and the 60s. And when we got into the 70s, the C programming language was really the one that really made everything take off, and that was the one that helped us develop the Unix and Linux operating systems. It was proprietary initially, and then became open source over time. And still to this day, many of our programming languages, including Python, which most of you are learning, share in the C and the C++ libraries that were developed way back then. So when somebody figured out an algorithm on how to do something, they would put it in a library, and many of our modern languages still pull from the same exact libraries. Isn't that interesting? But very important things happen. And the fact that we have this whole thing called the software stack, huge. In fact, this graphic, and we have it in the core shell too, shows kind of how both operating systems work, where they deal kind of like on a hardware level, and then you have all these libraries and runtimes that allow the applications that sit above to communicate with the hardware directly. And a lot of the coding that we do will be at high levels, and then we push it down through the libraries and the runtime so it can run on the operating system. But it was this separated approach, rather than writing natively for the kernel, that allowed us to have a separate operating system and then applications that run on top. And now we're in this era where it's like, oh, I'm on my phone, I'll download another app, big deal, right? But it took a while to get there, and we benefit from it now. And application development in some ways is significantly easy to do, and in other ways still equally as complex as it ever was. But we have the advantage that we can work at a high level. We don't have to build the code that talks directly to the hardware. We have special geeks that do that. We write the code that usually sits up on top here when we're coding. And I think that's really important. They talk about YouTube as an example, so like when we look at YouTube, here we have this platform that delivers videos to us. Now we completely take it for granted, but it was not that long ago that this was a completely revolutionary concept. And now we've gotten to the point where many of us, myself included, it's like, why do I need a TV set or cable TV or any of that stuff, right? Heck, a lot of us just do all of our watching through YouTube. Or we don't even bother watching regular TV anymore. We'll subscribe to a channel on YouTube, and it's all happening at this high level. Of course, in the background, there's some very sophisticated things going on because of that software stack. And so we are pushing through a browser, complicated software. Nobody has to install anything. All you need is the browser. As long as you have an internet connection, you can get to it. And so from a user standpoint, we're really getting to this era now where the technology has become transparent. And I think that's pretty important. Next little thing that they go into here, which I think is interesting, is talking about the terminology and knowing the right words. And frankly, one of the reasons you take this class is you go into IT and people start throwing around acronyms left and right. And you probably have heard a few from me tonight, and you're like, what the heck is FTP? Or whatever acronym I'm that way about acronyms in people's text messages. And I'm like, what is I know what LOL is, right? But I'm a little more like old school. When I'm on a text message, I type out the whole thing and have correct punctuation and spelling. That's not my way to communicate on text. Other people send me their acronyms, and I'm like, what does that mean? And I have to Google it literally, which is pretty sad. But it kind of shows my age a little bit too. But knowing the right words in IT is important, because when you walk into a job interview, for example, I can tell very quickly how knowledgeable somebody is on IT just by the way they talk about technology. And if you show me your computer screen, I can tell even more. But the terminology you use often will be the thing that sells you. And it doesn't mean that you have to master the technology, but even just knowing how to speak the terms puts you in a different category immediately. And so one thing you will have as a big takeaway here is to know the right words for very simple things. And so they have a couple of different words here. Just for example, these words, these are very common in IT. And these aren't acronyms, these are just full-on words. What the heck is a processor? What do you think? Somebody describe a processor to me.
It takes input, and then it does the computations, and then it's what tells the hardware and the software how to interact and give you the desired output.
Okay. You guys like his explanation? You think that's pretty good? It's pretty correct, right? Does anybody disagree? Really the processor, it on its own, right, without a software instruction set is, I always say it's a dumb machine. You still have to have the software to tell it what to do, ultimately. But yes, it does allow us to perform all the basic operations of the computer. It interfaces with the hardware. It crunches the numbers. It allows us to move data around. It allows us to store data. It all travels through the processor. Kind of the heart of the computer system. A lot of people will call the processor what? What's the acronym for a processor?
CPU.
CPU, which stands for Central Processing Unit. Now, of course, that has an implication. If there's a central one, there must be an auxiliary one or an adjacent one or something. And believe it or not, on old computer systems, we often would have separate processors for different things. So, for example, gamers, right, you have a CPU and a GPU, typically. Like a good gamer will go out and buy a great graphics card, and that has its own processor on board. So when you go out and you want a game, the reason you buy a video card is because it has a processor, in some cases, that's much more powerful than the CPU on your computer, and its only job is to process graphics, interestingly. Okay, so how would we define software? And you see the answers are on the subsequent slides, by the way. It's not like a mystery. But, all right, don't all jump in at once. I'll go right to the slide. It contains the instructions from which form applications, right? It's the instruction set. Software is just simply a set of instructions for the computer on how to perform its tasks. And as you guys are in, I know you're probably taking a Python class right now, or maybe have already taken it. You will learn that we do exactly that. You come up with a set of instructions and you tell the computer what to do. What about this word, algorithm? and this is a bizarre word because you maybe have heard people throw it around, but an algorithm is really a set series of steps known to produce a certain result. So for example, if I know how to make scrambled eggs, I have a routine where I heat up the pan, put in some oil, crack the egg, stir them up a little bit, cook them, flip them, put them on the plate. Now, for stupid as that sounds, that is an algorithm for making scrambled eggs. And so, in a computer sense, an algorithm is a set of instructions that are designed to perform a specific task, typically. And so, coding is all about creating algorithms and having, optimally the best solution to do something. All right.
So, hi.
Yes, Cindy Lou.
I had a situation today at work that, as far as knowing terminology, I know I'm not as proficient at it as some, but I know enough to be dangerous that I had to go online. We had an issue in our ERP system, and I had to go online and use their knowledge base, and I could not find what I needed. And I'm sure it's because, I thought I was using the terminology based on our ERP system, but I could not get an answer to my question. And, it's when that's all that you have at your fingertips is a knowledge base or, the frequently asked questions without logging a support ticket and waiting a couple days for an answer. It's very, very frustrating.
It is. And you know what most IT people do at that point when they're in that situation? What'd you say?
I said they Google it.
You got it. Because sometimes, and I kid you not, there's so many times where I'm running a piece of software, and let's say I'm in PowerPoint and I don't know how to, and I go to their help, and I'm like, this is useless. I jump out on Google and type the same question, and it's like, oh, there it is. And somebody's got a video on showing me how to do it at the same time. And you know what? That's one of the big secrets of IT, right? Especially in support roles, is masterful Googling. Knowing where to find information and knowing what information is good and what information is not. And that sounds really dumb, and our kids take it for granted. We're like, geez, Dad, Google it, All right, we'll Google it. And maybe the answer, Cindy Lou, maybe you could have found the answer that way. But, even if you couldn't, you might have gotten closer. I would bet that if you Googled the same problem, just did a straight Google search, you'd probably get a better answer than going to their knowledge base. Because
that thought did run through my mind, and I thought, I'm not gonna, because this is I was looking for where I could find stored jobs within our ERP system.
I see.
And so I thought, it might be a little specific.
You would be surprised.
I know, you're right. You're absolutely
You would be absolutely surprised, because the fun thing about IT people is this, right? We're on the computer all day long. And so we're much more apt to share knowledge with each other than other disciplines, and time after time I found like especially if I'm coding, I'll end up on like Stack Overflow or YouTube or something, and somebody's got the answer, and I'm always amazed at how accurate sometimes these things are, and I think that some large corporations could learn from that, but people have conversations. Sometimes they don't want to go into the knowledge base or whatever, and a company doesn't want to admit that they have a problem, or they don't want you to know where that information is stored, because then you won't call them for support and pay them more money.
Right.
So you got to think of the impetus for why they do that. Let's move on to this next thing where they talk about some ideas, and they talk about the concept of what abstract means and what abstractions are. And I'm not really too hung up on this as a concept, but I do think it's important to understand that we are moving into an era, by the way, where voice control and automated programming and things like that are going to start happening. And in fact, it's already happening. And you guys can leverage that. You can be intimidated by it, or you can leverage it. My thought is you always leverage it to your advantage. But when you abstract something, it really is kind of to think about it in a different way, so to separate it basically from some of its core components and think of the idea. And they talk about it here, so I don't feel compelled to really explain it to you because I know you can read it. They also talk about generalize and generalization. I think those are pretty common sense too. But here's another one I think that's maybe a little more interesting, operationally attuned. And this is not a concept you see thrown around a lot, but it says the ability to apply what we know about a device or how a system works to simplify its use. And, so their example I think is kind of neat. It says, past experience, loosen the lid by turning it left and tighten it by turning it right. And how do we know this? Because that's what happens. And then you encounter, it's like the screws are the same way, right? And then you encounter that one screw that threads the opposite way, like you're fixing a fan, and the fan screws tighten the other way. Talk about a mind bender. Like I'm trying to listen to this, what the hell? And then, you're just like so, tuned in to doing it a certain way. Or the guitar players in the room here, right? We learned to play the guitar with these fingers, the left hand on the fretboard and the right hand strumming, right, or picking. Try flipping that once and try to play. We are so attuned to going the other way, we can't even conceptualize doing it this way.
That's how I play all the time. Because I'm a lefty.
Oh, you are. You're a southpaw.
Yeah.
Fantastic. All right, Jimi Hendrix.
Don't go that far.
Well, the funny thing is, when you play right-handed on the guitar, I feel that's more of a left-handed thing than a right-handed thing, honestly, because more of the dexterity comes in your left hand than your right.
Yeah, definitely.
It takes a different kind of brain thinking, too. Here's another one. Have you ever heard this word, mnemonic, and what this means? And you know what? This is not a thing that I ever employed to try to remember things, real frankly. That's not how my brain works. But my wife thinks this way quite a bit. And she says, well, I think about this concept like this, and she thinks about something that's not related to it, that sounds like it, or spelled like it, or looks like it, or something like that, and that's how she remembers things, which I think is fascinating. That's not how my brain works. But it can work, and honestly, you can apply that to IT if that helps you to remember terms. But they give the example of like trying to remember all the Great Lakes. And so if you remember homes, I don't know how I would associate Great Lakes with homes, but whatever. My home is on a Great Lake, I guess, because I'm blocks from the lake where I live. But, I would just, my way of doing it is I would just think of a map visually and remember the lakes. That's me, right? Some people can't do that because they don't know which one is which, right? But I'm one of those geeks that would study maps as a kid. Now, the grand summary here is we did talk about all the things that are required in this chapter. And, does anybody have any thoughts, anything they want to throw in about any of this that they think is interesting? Or maybe I didn't cover it in enough depth? Okay. All right. So I'll take that as a no. I'm going to stop the video recording here. And then we're going to open it up to some different things here. So the video ends here.